Hi, I'm Kashish Vazirani from EL6303 Fall 15, and today I'm going to solve Homework 6 for Fall 2015, question 1. So the question is that x and y have joint density function, and the density function is given to us, and then there are 5 sub-questions to it. So first, looking at the joint density function, f of xy is equal to 1 plus xy upon a, and they say that mod of x is less than 1 and mod of y is less than 1 and it is 0 otherwise. So what they mean by mod of x less than 1 is basically that x goes from minus 1 to 1, and mod of y less than 1, again y goes from minus 1 to 1. So our first question is find a so that the above defined is a valid joint density function. So for any function to be a valid joint density function, the integration of the PDF should be equal to 1. The area under the curve should be equal to 1. So, let's see, f of x, y, x comma y, dx, dy should be equal to 1, y going from minus 1 to 1, and x going from minus 1 to 1. So, the question here is 1 upon a integral y going from minus 1 to 1, x going from minus 1 to 1, 1 plus xy should be equal to 1. On solving this, so first you keep the limits integration of y as it is and integrate over x. So when you're integrating over x in this term specifically, y will be treated as a constant. So you get x plus y x squared by 2 minus 1 to 1. On applying the limits, you will get 1 plus y by 2 plus 1 minus y by 2, y by 2, y by 2 will get cancelled and you'll be left with 2. And then integrate over y, and you're going to get 2y going from minus 1 to 1, which will be equal to a. And once you apply the limits, you're going to get a is equal to 4. So now, so that was question 1, part 1. Part 2 is, are x and y uncorrelated? Show your answer. So we know that the covariance and correlation coefficients are related, but to find the covariance we need to find the mu of x and mu of y and mu of xy, and we'll see the formula later. But first, finding mu of x, which is basically the mean of x. So to find mu of x, all you're going to do is you are going to integrate f of xy, which is the joint PDF of xy, multiplied by x over dx and dy, basically over x and y. So integral of y going from minus 1 to 1, x going from minus 1 to 1, x excuse me, x into 1 plus xy divided by 4 dx dy. So first integrating over dx will give us this, and then integrating over dy gives us 0. Similarly, we find the mean of y, mu y, and again, but just the only difference is that instead of x here we have y, so y fx y dx dy. Another way to do this, so I've done this in another way. Another way to do it is to first find the marginal density of y, and then put it in the formula of E of y, which is y f of y. So first finding f of y, again minus 1 to 1 fxy dx, f of y 1 upon 4x going from minus 1 to 1, 1 plus xy ds. How do you find f of y from the joint density function is basically that you remove the x component. That's why you're integrating this over x. And once you solve this, which is a very easy integration, you're going to get f of y is equal to half. And then from this we find the mean, and the mean E of y is y f of y going from minus 1 to 1, and you're going to get it's equal to 0. Now we know E of x is equal to 0 and E of y is equal to 0. Now we have to find E of xy, because that's what we need to apply in our formula for covariance, and once we know the covariance, only then can we find the correlation coefficient, and we're asked if x and y are uncorrelated or not. So to find E of xy, we basically use the formula where E x raised to m y raised to n is used. So there's a formula which says E x raised to m y raised to n integrated over x raised to m y raised to n f of xy dx dy. So here our m is equal to 1 and n is equal to 1. So it's simply xy 1 plus xy upon 4 dx dy. And once you solve this integral, you're going to get e of xy is 1 upon 9. So the like I said, covariance is dependent upon these three factors. So covariance of xy is e of xy, that is the mean of xy together, minus mean of x into mean of y. Mean of x and mean of y was 0, so 1 by 9 minus 0, you're going to get 1 by 9. Now, correlation factor is basically covariance divided by the variance, root of variance of x and I'm sorry. So basically we know variance of x and variance of y is sigma x square and sigma y square. So the correlation is equal to covariance divided by sigma x sigma y. And we know that sigma x and sigma y are values that are always greater than 0. So that's why since covariance is not equal to 0 and the denominator is always greater than 0, we get rho of xy is greater than is not equal to 0, sorry. So we get rho xy is not equal to 0 since covariance is not equal to 0 and sigma x is greater than 0 and sigma y is greater than 0. That's why since the correlation factor is not equal to 0, x and y are not uncorrelated. Had this been equal to 0, x and y would be uncorrelated. Sorry. Are x and y independent? Now, the one property that we must keep in mind while solving this is that just because x and y are not correlated does not mean they are not independent or independent. You cannot decide independence on the basis of correlation, and but the other way around is true. If you know whether x and y are independent or not, you can decide whether they are uncorrelated or not. So anyway, finding if x and y are independent, the basic definition of independence would be basically satisfied if e of xy is equal to e of x into e of y. But we know e of xy is 1 by 9 and e of x into e of y is 0 into 0, and 1 by 9 is not equal to 0, therefore they are not independent. Now the third question is, the fourth question is, find the joint density function of x square and y square. So now you let z be equal to x square and w or omega be equal to y square. So first, so the formula for this is basically f z omega is equal to 1 upon the Jacobian into fxy. So anyway, first we find the Jacobian. So Jacobian is basically dz divided by dz by dx, dz dy, d omega dx, d omega dy. And when you solve this, dz by dx is easy, so it's basically d by dx of x square, so that's equal to 2x. dz by dy is d by dy of again x square, which is equal to 0. D by dy of y square is equal to 2y, and d by dx of y square is equal to 0. This into this minus this, so that's going to give you 4xy. So we know that Jacobian is equal to 4xy. Now, like I said, the formula is f z omega is 1 upon Jacobian fxy. So that's 1 upon 4xy into 1 upon 4, 1 plus xy. So that's going to give you 1 upon 16, 1 plus xy. But this is in terms of x and y. We need to find it in terms of z and omega. So we know that x square is equal to z, therefore x is equal to plus minus z. Y square is equal to omega, therefore y is equal to plus minus omega. Now we have 4 values in total because we have 2 values for z and 2 values for omega because y is equal to plus minus omega. So basically x and y can have the combinations root z root omega minus root z minus root omega, root z minus root omega minus root z plus root omega. Now when you apply these values in this, you're going to get the answer and you're going to add all of these. So 1 plus xy at this value, 1 plus 1 plus xy at this value, plus 1 plus xy at this, and plus 1 plus xy at the last value, and the values will also be put into this multiplication of xy in the denominator. So once you solve this entire function, you're going to get 1 by 4 root z omega. So that's your answer for the joint PDF of x square and y square. F z omega is z comma f z omega is equal to 1 upon 4 root z omega. Now the last part, prove or disprove x square and y square are independent. So we know x square is equal to z, y square is equal to omega. So we're checking for independence of z and omega basically. Now a property we discussed earlier was that e of zy is equal to e of z into e of y if they're independent. Also f of z omega is equal to f of z into f of omega if they're independent. So you find f of z by integrating f of z omega over omega, and that will give you 1 upon 2 z omega. Similarly, f of omega will give you 1 upon 2 omega. And when you multiply these two, you'll get 1 upon 4 root z omega. So we know f of z omega is 1 upon 4 root z omega. We know f of z is 1 upon 2 root omega. And we know f of omega is 1 upon 2 root... I think I've inverted this while writing. I'm sorry. F of omega is 1 upon 2 root omega. F of z is 1 upon 2 root z, like we found out here. F of omega is 1 upon 2 root omega and f of z is 1 upon 2 root z. And when you multiply these two, you're going to get f of z omega. That's why x square and y square are independent. Thank you.